At very, very fast speeds, classical relativity breaks down. But this wouldn't be clear until scientists began flying Sopwith camels and examining the nature of the fastest known thing, light. In the middle of the 19th century, it had been known for quite some time that electricity could be used to make a magnet, and that magnets could be used to make electricity. But the man who made the first color photograph, James Clerk Maxwell, unified everything known about electricity and magnetism in 4 magnificent equations. And these equations described an electromagnetic wave that would travel through the empty space at exactly the measured speed of light. And in fact, this wave was light. According to Maxwell, light was an electromagnetic wave that moved through empty space with a speed of 186,000 miles per second. But from the standpoint of relativity, the question naturally arises, relative to what? The equation seemed to say that light moved at 186,000 miles per second relative to everything. This was a dilemma facing the physicists at the turn of the 20th century. If Maxwell was right, then light moves with a velocity of c, 186,000 miles per second, always. But if classical relativity was right, there is no absolute velocities, and the velocity of light should depend on who is doing the measuring and their motion relative to the source of the light. How could both be right? Either our understanding of motion or our understanding of electromagnetism and light were in jeopardy. The very foundation of physics was facing a crisis. A 26-year-old patent clerk named Albert Einstein would provide the way out of this crisis. Einstein accepted both of these seemingly contradictory notions and changed the course of science. He accepted the idea of relative motion, but restated it as follows. Any person moving at a constant velocity will observe the same laws of physics that a stationary person observes. And since the speed of light is part of the laws of physics, Einstein postulated that all observers will measure the same speed of light, regardless of their state of motion. But speed is just a measure of distance moved in a given time. And in order to agree on the speed of light, different observers might have to disagree about distance and time. You may have heard the term light year, used in astronomy or cosmology. A light year is the distance that light travels in 1 year, about 6 trillion miles. So you could say that the speed of light is 1 light year, a distance, per year, a measure of time. You could just as easily say a light second is the distance that light travels in 1 second. About 186,000 miles. And so the speed of light is 1 light second, a distance, per second, a measure of time. Here are 2 starships, one at rest and the other in motion. When the moving ship passes a stationary ship, each fires its laser. Now, according to Einstein, the speed of the laser light doesn't depend on the motion of the ship. So we see both beams traveling side by side at the same speed. The crew of the ship at rest witnessed their laser beam traveling 12 light seconds in 12 seconds, and report that light travels at the speed of 1 light second per second. Correct. But what about the beam from the moving ship? Does it travel only 6 light seconds in 12 seconds? If so, the crew on board the moving vessel would report that light travels at only half speed? No, they wouldn't. But why not? According to Einstein, light always travels at 1 light second per second, regardless of the motion of the person who measures it. How do we fix our picture so that this is right? Part of the answer lies in the fact that the clocks on the moving ship slow down. As we stated earlier, if we must agree on the speed of light, we may have to disagree on the measure of time. If the clocks on board the moving vessel ran only half as fast as the ones at rest, our problem would be completely solved. The light beam from the moving ship would still travel 6 light seconds, and with the slow clocks, it would take only 6 seconds for this to happen. And the crew would report that light travels at precisely 1 light second per second. But it turns out the clocks don't slow down enough to be the whole answer. So in a minute, we'll look at the second part of the answer.
And of course, this isn't a statement about clocks. It is time itself that slows down. Right? Over the last 100 years, countless experiments have shown without a doubt that it is time itself that slows down. But why does it occur?
A clock is any device that counts events that occur at regular intervals. The event that drives a clock can be just about anything. The swing of a pendulum, the bounce of a ball, the unwinding of a spring, or the changing current in an electric circuit. Any regular event will do. Let's imagine constructing a clock in which a beam of light bounces between 2 mirrors. Whenever the light strikes the bottom plate, the clock advances. The advantage of using this kind of clock is that we can be sure that the observer who looks at the clock will see the timing mechanism, the beam of light, moving at the same speed. If 2 such clocks are stationary, then we would expect the time indicated on each clock to be precisely the same. But what happens when one clock is in motion? Notice although both clocks are identical, the moving clock ticks slower than the one at rest. In order to understand why, notice the paths of the light beams. The light in the stationary clock travels up and down vertically, but the light beam in the moving clock must travel a longer diagonal path. Since both beams travel at the same speed, and the upper beam travels a longer distance, the stationary observer sees the moving clock run slower than his own. This slowing down of clocks in motion is known as time dilation. It should be stressed that a person moving along with the moving clock would notice nothing unusual at all. The clock and the flow of time would seem to progress normally. According to this observer, he is at rest and the other observer is moving past him. According to him, it is the other clock that is running slowly. The flow of time in Einstein's universe is entirely relative.